When you think about the ideal stream, what do you think of? Is it cheerful and beautiful? Healthy and clean? What does the landscape around it look like? Now think about the waterways around Athens. Perhaps you've seen streams along Lake Herrick, Tanyard Branch, or the Oconee River. What do they look like? How are they different from the one you just imagined? It's likely that our local water networks seem a bit degraded by comparison, but perhaps it's hard to put a finger on why, or how one might go about bringing them closer to the ideal. This module has been designed to help you learn about stream restoration opportunities. In it, we'll discuss watersheds, impairment, general stream classification, and restoration techniques. Be sure to take a look at the glossary sheet attached to this module if you notice us using any unfamiliar terms. To begin with, we'll provide a little environmental context with a discussion on watersheds, including what they are, considerations that ought to be made when mitigating impairment within a watershed, and how land cover affects the quality within a given area.
A watershed is an area of land bounded by a hydrologic system in which all living things are inextricably linked by a common water source. All land uses have an effect on water quality, whether positive or negative. In forested areas with good vegetation, most rainfall is able to soak into the soil and has little runoff. Stream flows are fairly steady and water quality is good. In urban areas, high amounts of impervious surfaces allow little rainfall to infiltrate into the soil, causing high runoff and flooding, stream flows with high peaks and low flows in between, and poor water quality. In addition, soil erosion increases due to lack of vegetation to hold the soil down. Higher storm runoff is usually the biggest factor in urban development. This creates a high peak flow rates that damages streams and habitats. Each watershed is unique, and there are many factors that need to be considered with the overall goal to improve the quality of all resources throughout the watershed. Considerations include habitat requirements for sensitive species, habitat loss and conversion trends, sources of impairment, requirements for a variety of topics such as stormwater management and habitat conservation. Before any plan can be implemented, an inventory of historic and existing aquatic and terrestrial species needs documenting, and prioritization of restoration, establishment, and enhancement activities. Information needs include current trends in habitat loss or conversion, cumulative impacts of past development activities, current development trends, site conditions that favor or hinder success, chronic environmental problems such as flooding and poor water quality, and knowledge of the necessary permits.
Through our discussion on watersheds, we can see how streams fit into larger environmental networks. However, it's important to remember that they're also complex systems unto themselves. With so many different ecological considerations to take in, it may seem daunting to try to determine if a waterway is functioning properly or not. Next, we'll talk about how to tell whether a stream is impaired.
The Clean Water Act of 1972 requires that states develop and maintain water quality standards that govern the physical, chemical, and biological aspects of streams. These standards are different in Georgia for brackish and freshwater. We'll look specifically at freshwater standards because they apply to the vast majority of streams. By using the guidelines provided in the Clean Water Act and Georgia's own water quality standards, we can determine if a stream is impaired or not. Georgia requires that all waters be free from materials associated with municipal or domestic sewage, as well as industrial waste. These include noticeable deposits of sludge, scum, and floating debris, as well as any discharges producing negative changes in turbidity, color, odor, temperature, taste, or other objectionable conditions which interfere with legitimate water uses. Also important are the chemical characteristics of water. Some inorganic compounds fall under very specific maximums set by the government. Broader means of measuring water quality include pH levels, alkalinity, hardness, total dissolved solids, conductivity, sodium absorption, and radioactivity. Organic chemicals are also measured. These include the levels of carbon in the water as well as the levels of dissolved gases. Lastly, we must examine the biological characteristics of the stream. These include the types of microorganisms, like bacteria, viruses, and protozoa in the water, as well as the presence of larger organisms like aquatic plants, fish, crustaceans, and worms. By examining the stream and comparing it to the standards set by the Clean Water Act as well as Georgia's own Department of Environmental Protection, we can determine whether or not it is impaired. In fact, this is the exact same process conducted by Georgia's Department of Environmental Protection every 5 years as they undergo periodic assessments of impaired waterways statewide.
It's time to focus on the general classifications of the different types of stream reaches. Getting to know these patterns will help us determine the condition of any stream, decide whether it is a good candidate for restoration, and envision its appearance and functional properties after restoration.
Before beginning restoration on a stream, it's necessary to classify the stream's current condition and identify an ideal condition or a reference condition. When using natural channel design, streams are broadly classified as types A through G by their level of entrenchment, width and depth, and sinuosity. Within each category, streams are further classified by considering their slope range and channel material. After a disturbance, many streams change form. This is often referred to as channel evolution. According to Andrew Simon's channel evolution model, change is initiated once a stable stream is disturbed by an event such as channelization, urbanization, or removal of streamside vegetation. A disturbance leads to channel degradation and entrenchment. Over time, entrenchment leads to steepening of the banks, which ultimately causes the banks to fail and the channel to widen. Erosion continues upstream, funneling sediment downstream, and eventually a new low-flow channel will begin to form in the sediment deposits. The end of the channel evolution process is characterized by a stable stream with a dimension, pattern, and profile similar to those of undisturbed channels. The new channel is at a lower elevation than its original form, and the old floodplain has become a dry terrace.
Stream classification provides us a method to characterize and compare stream reaches, and ultimately evaluate whether or not a stream needs enhancement or restoration. The first steps of any stream restoration project is to evaluate the watershed and characterize the existing conditions of the stream reach. One method adopted by regulators is called natural channel design. The stream reach is characterized by identifying bankful elevation and surveying a cross-section and longitudinal profiles. This involves measuring the stream width, depth, relationship to floodplain, and channel sinuosity. From these measurements, we calculated the stream-channel ratios necessary to classify the channel. These include the entrenchment ratio, width-depth ratio, sinuosity, slope, and channel material. Based on these values, we classified a stream reach that drains into Lake Herrick. According to the natural channel design classification, the stream has little access to the floodplain at bankful elevation, causing it to be incised with steep eroding banks. Here, you can see the steep banks in active erosion. Now that we've classified our stream, we need to determine whether or not it needs restoration. To do this, you must characterize the watershed and valley type to determine stability. Then, find a reference stream reach for comparison and compare to regional reference curves. Ideally, you would find a stream in your area, classify it, and compare it against other streams. However, an ideal reference does not always exist. Instead, we refer to the best stream reaches in the area and compare it to regional and mini curves. Because there are no watersheds and streams in the Athens-Clarke County area that are completely undisturbed, we compared our measurements to other stable streams, such as reaches out at Tallahassee Creek, which is a relatively undisturbed stream system and the closest we can get to reference stream. Once we have identified a reference stream reach, we can classify it. According to others, one reach in Tallahassee Creek is a C stream type. This stream type is common in Piedmont streams in the southeast. C streams are meandering streams with access to their floodplain and have pools in the meanders. Access to the floodplain reduces excessive bank erosion and promotes floodplain function that allows the stream to spread across the floodplain and deposit sediment and nutrients.
Now we know what types of waterways we're dealing with. But what implications does this information have for restoration potential? And how do we actually restore a stream? Next, we'll talk about some of the different options there are, including raising a stream bed to its floodplain, bringing a floodplain down to its channel, putting in a bank-full bench, and bank stabilization and armoring.
So if you're doing stream restoration based on natural channel design, then there are 4 approaches you need to be familiar with. And these approaches are numbered 1 through 4, and they're prioritized, so 1 is the most desirable and 4 is the least desirable. So if you have a stream that's becoming incised with steep banks, the first priority would be to actually raise the stream bed back to its original height so that the stream, when it floods, can reconnect with its original floodplain. So this is advantageous for several reasons. First, by raising the stream bed up to its pre-impairment height, the stream can reconnect with its original floodplain. Additionally, by raising an incised stream, a restoration project can also raise the groundwater table, which may restore or enhance the wetland conditions in the floodplain. Now, this can be accomplished by excavating a new channel. The new channel stream bed will be at a higher elevation than the existing stream bed and designed that the stream can flow out of its banks and into the floodplain during a flood event. The bank slopes, distance between pools and riffles, and meander lengths are designed based off a reference stream. The new stream will not be parallel to the old stream, which may have already lost its meanders, but will meander across the entire floodplain, even if it cuts across the old channel. Where it crosses the old stream, channel plugs are used during construction to direct the stream flow into the new bed. The original stream bed can then be left alone or partially filled in so that it becomes a pool or wetland within the floodplain. Once the new stream bed is created, the existing stream is diverted into the new one. The second priority would be to take the floodplain down to the existing stream height. This involves creating a new stable stream bed and floodplain at the elevation of the current stream. This is done by excavating a new floodplain and stream channel at the elevation of the existing incised stream. The new channel is typically an E or C stream, with the bankfull stage located at the elevation of the newly excavated floodplain. These projects typically decrease the potential for flooding, and the newly constructed stream corridor created by the excavated floodplain may enhance riparian wetlands.
The potential for erosion increases as stream bank height increases. Incised and eroding streams should be graded to include a bank full bench. In order to reduce shear stress at the existing channel elevation, the Stream Restoration Guidebook recommends excavating a floodplain bench on one or both sides of the existing channel at existing bank full stage. The resulting channel is typically a low slope stream, with the bank full stage located at the elevation of the newly widened floodplain. This restoration approach does not increase sinuosity to a large extent because of land constraints, but can produce a stream with long-term stability if designed properly. This approach may require more structural measures and maintenance than other restoration approaches. The last method to be considered for a stream restoration involves stabilizing a stream bank in place. This is often done by armoring the bank with materials like riprap, concrete, gabions, or other types of structures. This method is given the lowest priority status because, as these projects do not correct stream pattern, dimension, and profile, the stream banks will continue to be susceptible to stress and erosion. Finally, stream bank armoring may negatively impact the health of a stream downstream of the project site. This is because armored banks may allow for more concentrated and higher velocity flows that can cause downstream erosion. For an example of an armored stream, look at the stretch of Tanyard Creek behind Bolton Dining Hall.
Riparian buffer zones are vital for good water quality. The term riparian buffer is used to describe lands adjacent to stream banks where the vegetation is strongly influenced by the presence of water. They are also known as vegetated buffer zones. Riparian buffers often contain native grasses, flowers, shrubs, and trees that line the stream banks. A healthy riparian area is evidence of wise land use management. Degraded riparian buffers reduce water quality values, reduce wildlife and fish populations, and can cause property damage by bank erosion. Removal of riparian vegetation results in increased water temperatures and decreased dissolved oxygen. Loss of riparian vegetation causes stream bank erosion. Eroding banks contribute to sedimentation and lead to a wide, shallow stream with little habitat value. These factors result in significant reductions in aquatic stream life.
All right. Now you gotta go to the second one that goes probably after Ben.
Yep. Then I have to look at you.
Yeah.
Rehabilitating riparian buffers is key to restoring natural stream functions in aquatic habitats. Such as, okay. Rehabilitating.
Look at the camera, then start.
Rehabilitating riparian buffers is vital. Rehabilitating riparian buffers, channel stabilization, improved water quality, improved wildlife and fish populations, improved aesthetics, and other associated values. Riparian zones help to reduce sediment, nitrogen, phosphorus, pesticides, and other damaging pollutants from reaching a stream. They are most effective at improving water quality when they include native grasses or herbaceous filter strips, along with deep-rooted trees and shrubs along the stream bank. Riparian vegetation is a major source of energy and nutrients for stream communities. They are especially important in small headwater streams where up to 99% of the energy input may be from woody debris and leaf litter. They are especially important in small headwater streams where up to 99% of the energy input may be from woody debris and leaf litter. Riparian buffers provide valuable habitat for wildlife, and the overhanging riparian vegetation also keeps streams cool. Depending on the surrounding land use and the area topography, riparian buffers should range from 25 to 100 feet wide on each side of the stream. Recommended practices for restoring riparian areas include protecting or establishing native shrubs, trees, and other vegetation along the stream that help prevent bank erosion, trap sediment, and filter other pollutants. Riparian buffers consist of vegetation that is highly influenced by the presence of water. There are certain species that are indicative of a healthy and stable stream bank. These species may also be used to restore riparian areas. Such species here in the Piedmont area include sycamores, red maples, water oaks, and river birches. Shrubs include sweet shrubs, buttonbush, and common serviceberries. Herbaceous plants include jack-in-the-pulpit, swamp sunflower, cardinal flower, Joe pieweed, and other vegetation. These plants not only are important to the physiological makeup of a riparian area, but are also commonly used in landscaping due to their beautiful features. Therefore, riparian areas may be just as beautiful as they are functional.
As you can see, there are a lot of considerations to be taken into account for successful stream restoration. We've covered many of them in this module, from mitigation techniques concerning the greater watershed, to how to determine whether or not a stream is impaired, to stream classification and restoration methods. Take a look at the glossary sheet attached to this module for terms you may not have been familiar with, and use it to help you complete the lab learning component.